Maria Telkes was born on December 12, 1900, in Budapest, Hungary, into a family that valued education and intellectual achievement. Her father, Aladar Telkes, was a government administrator, and her mother, Maria Labanda Telkes, came from a cultured, educated family. The Telkes household was comfortable middle class, not wealthy, but with enough resources to provide their children with excellent education and exposure to ideas, science, and culture. Young Maria grew up in turn-of-the-century Budapest, a city that was part of the Austro-Hungarian Empire and was experiencing rapid modernization and intellectual ferment. From early childhood, Maria showed exceptional aptitude for science and mathematics. She was curious about how things worked, fascinated by chemistry and physics, and drawn to understanding the natural world through systematic investigation. Her parents, unusually progressive for the era, encouraged their daughter's scientific interests rather than steering her toward traditional feminine pursuits. They arranged for her to attend excellent schools and supported her ambition to study science at university, still a rare path for women in early 20th century Europe. Maria attended the University of Budapest, studying physical chemistry. This was during World War I and its aftermath, a turbulent period in Hungarian history marked by war, revolution, and political upheaval. The Austro-Hungarian Empire collapsed in 1918, Hungary briefly became a communist republic in 1919, then experienced conservative counter-revolution. Through this chaos, Maria focused on her studies, graduating in 1920 with a degree in physical chemistry. She then continued for doctoral studies, earning her PhD in 1924 at age 23 with a dissertation on the physical chemistry of metallic alloys. Her doctoral research was excellent, demonstrating sophisticated understanding of thermodynamics, materials science, and experimental techniques. But as a newly minted PhD in chemistry in 1920s Hungary, Telkes faced limited career prospects. Academic positions for women were rare. Industrial research jobs were scarce in post-war Hungary's struggling economy. And the political situation remained unstable, with authoritarian government, economic hardship, and increasing restrictions on intellectual freedom. Like many talented young people, Telkes began thinking about leaving Hungary for better opportunities elsewhere. In 1925, at age 24, Telkes immigrated to the United States, joining relatives who had already settled there. She arrived in America speaking limited English, holding a Hungarian PhD that American employers might not recognize, and facing the challenges that all immigrants encountered. But she also had exceptional scientific training, determination, and the confidence that she could contribute meaningfully to research if given the opportunity. She was not going to waste her education or her abilities. Telkes's first American position was at the Cleveland Clinic in Ohio, working as a biophysicist researching medical applications of chemistry and physics. This might seem tangential to her training in physical chemistry, but it allowed her to use her experimental skills, gain experience in American research settings, and improve her English. She worked on problems involving energy metabolism, physiological measurements, and the physical chemistry of biological systems. The work was interesting and gave her valuable experience in applied research, taking theoretical knowledge and using it to solve practical problems. Through the late 1920s and 1930s, Telkes built her scientific reputation in the United States. She published research papers, gained recognition for her experimental skills, and established herself as a capable researcher who could work across disciplinary boundaries: chemistry, physics, biology, engineering. She became a U.S. citizen, putting down permanent roots in her adopted country, and she began to focus on the research problem that would define her career: how to harness solar energy effectively for practical applications. When the United States entered World War II in 1941, scientific research was mobilized for the war effort. Researchers across the country were recruited to work on military problems: radar, explosives, materials, medicine, and countless other challenges. Maria Telkes, now an established researcher with expertise in physical chemistry and biophysics, joined this effort. In 1941, she was appointed to a position at the Massachusetts Institute of Technology, MIT, working in the newly formed Solar Energy Conversion Project. Why solar energy during a war? Because the military recognized that soldiers fighting in remote locations, Pacific islands, deserts, jungles, needed portable, reliable sources of energy and fresh water. Conventional fuel supplies were vulnerable to disruption, and transporting fuel to remote locations was dangerous and expensive. Solar energy, if it could be harnessed effectively, offered a solution, an unlimited energy source available anywhere the sun shone, requiring no fuel supply lines, no complex machinery, no vulnerable infrastructure. Telkes's wartime assignment was to develop a solar-powered desalination device, a portable unit that could convert seawater or brackish water into fresh drinking water using only solar energy. This was a critical problem for naval operations, island garrisons, and survival situations. Shipwrecked sailors and downed pilots in the Pacific faced the terrible irony of being surrounded by water but having nothing to drink. A portable solar still could save lives. The technical challenge was substantial. Desalination requires energy to evaporate water, leaving salt and impurities behind, and a method to condense the water vapor back into liquid form. Solar stills had been proposed before, but they were generally inefficient, bulky, unreliable, or impractical for military use. Telkes needed to design a device that was efficient enough to produce adequate fresh water, compact and lightweight enough to be portable, robust enough to function in harsh conditions, and simple enough that soldiers with minimal training could use it. Telkes's design was ingenious in its simplicity and effectiveness. The solar still consisted of an inflatable plastic envelope with black fabric on the bottom to absorb solar radiation. Seawater was placed in the bottom of the envelope. As sunlight heated the black fabric, water evaporated, leaving salt behind. The water vapor condensed on the cooler plastic surface above and ran down into collection channels. The device produced several pints of fresh water per day, enough to keep a person alive in survival situations. The inflatable solar still was lightweight, about 2 pounds, compact when deflated, could fit in a life raft or survival kit, required no moving parts or filters, and worked reliably with minimal maintenance. It was a masterpiece of practical engineering, solving a real problem with elegant simplicity using fundamental physical chemistry principles. Telkes understood thermodynamics, heat transfer, vapor-liquid equilibrium, and materials properties, and she applied this knowledge to create a device that saved lives. The military adopted Telkes's solar still, and it was distributed to life rafts, survival kits, and emergency supplies throughout the U.S. Navy and other services. How many lives it saved is impossible to calculate precisely, but shipwrecked sailors and downed aviators in the Pacific used these stills to survive until rescue. Telkes's wartime contribution was practical, immediate, and life-saving, scientific knowledge translated directly into technology that solved critical problems. But Telkes wasn't satisfied with this one wartime application. She recognized that solar energy had far broader potential for heating buildings, generating electricity, cooking food, and countless other uses. If solar energy could be harnessed efficiently, it could reduce dependence on fossil fuels, provide energy to remote or undeveloped areas, and offer a clean, renewable alternative to coal and oil. These ideas were ahead of their time. In the 1940s, fossil fuels were cheap and abundant, and few people worried about their environmental impacts or future scarcity. But Telkes saw the potential for solar energy and dedicated the rest of her career to developing it. After World War II, Telkes continued her research at MIT, now focusing on solar heating for buildings. The challenge was to develop practical, economically viable systems that could heat homes using solar energy. Previous attempts at solar heating had largely failed because they were expensive, inefficient, or unreliable. Telkes believed she could do better by applying modern materials science and thermal engineering principles. The key innovation Telkes developed was a thermal storage system using phase change materials. The problem with solar heating is obvious. The sun only shines during the day, but buildings need heat at night and on cloudy days. You need a way to store solar energy collected during sunny periods and release it later when needed. Previous solar heating systems used water or rocks as thermal storage media, but these required large volumes to store meaningful amounts of heat. Telkes's solution was to use chemicals that undergo phase changes, solid to liquid or vice versa, at useful temperatures. When a material melts or solidifies, it absorbs or releases substantial amounts of heat, the latent heat of fusion. Telkes identified Glauber's salt, sodium sulfate decahydrate, as an ideal phase change material for solar heating. It melts at about 90 degrees Fahrenheit, 32 degrees Celsius, perfect for home heating, and has high latent heat, meaning it can store large amounts of thermal energy in relatively small volumes. Her thermal storage system worked like this. During sunny days, solar collectors, essentially insulated boxes with glass covers and black absorber plates, heated air or water. This heat was transferred to containers of Glauber's salt, melting the salt and storing energy as latent heat. At night or during cloudy periods, the salt solidified, releasing stored heat to warm the house. The system could store enough heat from a sunny day to provide warmth through cold nights, smoothing out the intermittent nature of solar energy. Telkes saw an opportunity to demonstrate this technology at full scale. She partnered with architect Eleanor Raymond to design and build a house heated entirely by solar energy. No conventional furnace, no backup heating system, just solar collectors and Telkes's thermal storage. The project was funded by Amelia Peabody, a sculptor and philanthropist interested in innovative architecture and sustainable living. The team was entirely female, a remarkable achievement in the 1940s engineering world dominated by men. In 1948, construction began on what would become known as the Dover Sun House, located in Dover, Massachusetts. The house featured large south-facing solar collectors mounted on the roof, a thermal storage system containing several tons of Glauber's salt, and distribution systems to circulate heat throughout the house. It was an ambitious experiment, attempting to prove that solar heating could work in cold New England winters, using technologies that had never been tested at this scale. The Dover Sun House was completed in 1949 and became an immediate sensation. It was featured in newspapers and magazines nationwide, presented as the house of the future that heated itself using only sunshine. Journalists, scientists, and curious members of the public visited to see this novel technology. Telkes became known as the Sun Queen, a nickname reflecting both her gender and her pioneering work harnessing solar energy. For the first winter, the system worked beautifully. The solar collectors gathered heat during sunny days, the Glauber's salt storage absorbed and held that heat, and the house remained comfortably warm even during cold Massachusetts nights and cloudy periods. It was a triumph, proof that solar heating could work, that renewable energy could replace fossil fuels for home heating, and that Telkes's innovative thermal storage system was effective. But problems emerged in subsequent winters. The Glauber's salt, despite Telkes's careful engineering, proved problematic for long-term use. The salt didn't always solidify uniformly. It could supercool, remain liquid below its freezing point, or separate into components with different melting points. These issues reduced storage efficiency and reliability. Additionally, there were disputes among the project team about how to address these problems and what modifications were needed. By 1953, the house was equipped with a conventional heating system as backup, and by the late 1950s, the solar heating system was essentially abandoned. The partial failure of the Dover Sun House was disappointing, but didn't discourage Telkes. She recognized that the thermal storage problems were technical challenges that could be solved through better understanding of phase change materials and improved system design. She continued researching thermal storage, working to develop more reliable phase change systems and alternative approaches to storing solar energy. Through the 1950s and 1960s, solar energy research faced skepticism and limited funding. Fossil fuels, oil, natural gas, and coal were cheap and abundant. The environmental movement hadn't yet emerged, climate change wasn't recognized as a concern, and few people saw compelling reasons to develop alternative energy sources. Solar energy was often dismissed as impractical, too expensive, suitable only for specialized applications like satellites or remote installations. But Telkes persisted. She moved from MIT to Princeton University, then to New York University's College of Engineering, and later to the University of Delaware and the Institute of Energy Conversion. At each institution, she continued researching solar energy applications: heating, cooling, electricity generation, water heating, and thermal storage. She published prolifically, received patents for her innovations, and gradually built the scientific foundation for practical solar energy systems. Telkes's work extended beyond heating systems. She developed solar ovens that could reach temperatures sufficient for cooking and sterilization, important for developing countries where fuel for cooking was expensive or unavailable. She worked on thermoelectric generators that could convert solar heat directly into electricity using thermoelectric materials. She researched solar-powered air conditioning and refrigeration, exploring whether buildings could be cooled using solar energy, a particularly valuable application in hot climates where cooling demand peaks when solar energy is most abundant. She also became an advocate for solar energy, giving lectures, writing articles, and consulting with governments and organizations interested in renewable energy. She argued that solar energy wasn't just technically feasible, but economically sensible and environmentally necessary. Her advocacy was ahead of its time. In the 1950s and 1960s, these arguments found limited audiences. But Telkes kept making the case, confident that eventually, circumstances would prove her right. Through these decades, Telkes received recognition for her contributions. She was elected to the Society of Women Engineers, received awards for her research, and was honored by professional organizations. But mainstream funding for solar energy research remained limited, and commercial applications remained rare. Solar energy was still seen as a curiosity, not a serious energy source. The 1970s changed everything. The 1973 oil crisis, when Arab oil-producing nations embargoed oil exports to the United States and other Western countries, suddenly made energy independence and alternative energy sources urgent national priorities. Oil prices quadrupled, gasoline became scarce, and Americans waited in long lines at gas stations. The crisis demonstrated the vulnerability of dependence on imported fossil fuels and created massive interest in domestic and renewable energy sources. Suddenly, solar energy research that had been languishing for lack of interest and funding became a national priority. The U.S. Department of Energy increased solar research funding dramatically. Private companies invested in solar technologies. Universities established solar energy research programs. And Maria Telkes, who had been working on solar energy for 3 decades, while most researchers ignored it, found herself at the center of renewed attention and interest. In the 1970s and 1980s, as solar energy finally received serious attention and investment, Telkes's pioneering work was increasingly recognized and celebrated. She had been right all along. Solar energy was practical, economically viable, especially as fossil fuel prices rose, and increasingly necessary. Her decades of research provided foundational knowledge that new researchers and engineers could build upon. In 1977, at age 76, Telkes received one of her most prestigious honors. She was awarded the first Solar Energy Society Achievement Award, later renamed the Charles Greeley Abbott Award, by the International Solar Energy Society. The award recognized her lifetime contributions to solar energy research and development. It was particularly meaningful because it came from her scientific peers, the community of solar energy researchers who understood the importance and difficulty of the work she had done. Telkes continued active research well into her 70s and 80s, an extraordinary sustained productivity over more than 5 decades. She worked as a research professor at the University of Delaware's Institute of Energy Conversion, where she mentored younger researchers, continued developing improved thermal storage materials, and contributed to projects developing solar heating and cooling systems for buildings. One of Telkes's important later contributions was her work on improved phase change materials for thermal storage. She experimented with various salts, waxes, and other materials that could store thermal energy through phase transitions. She developed additives and nucleating agents that could prevent supercooling and phase separation. the problems that had plagued the Glauber's salt system in the Dover Sun House. These improvements made phase-change thermal storage more reliable and practical for commercial applications. Telkes also worked on solar cooling systems, using solar heat to drive absorption refrigeration cycles that could cool buildings. This seemed paradoxical, using heat to create cooling, but it worked through clever thermodynamics. Absorption refrigeration uses heat to drive chemical processes that absorb heat from a space, creating cooling. By powering these systems with solar heat, you could use abundant sunshine to cool buildings when cooling demand was highest. Telkes developed systems demonstrating this principle and showed it could be economically competitive with conventional air conditioning in appropriate climates. Through these later decades, Telkes received numerous additional honors. She was inducted into the National Inventors Hall of Fame in 2012, posthumously. The Society of Women Engineers established a scholarship in her name. Articles and books about the history of solar energy prominently featured her contributions. She was increasingly recognized not just as a solar energy researcher, but as a pioneer whose work had laid foundations for an entire field. Telkes also became an inspiration for women in engineering and science. Her career demonstrated that women could succeed in technical fields, could make fundamental contributions, and could persist despite skepticism and barriers. She had worked in male-dominated environments throughout her career, had often been the only woman in research groups or at conferences, and had faced the subtle and not-so-subtle discrimination that women in STEM fields experienced. But she had never let these barriers stop her from doing excellent research or pursuing her vision of practical solar energy. In interviews late in her life, Telkes was characteristically modest about her achievements. She emphasized that solar energy development had been a collaborative effort involving many researchers, that her contributions were part of a larger movement, and that much work remained to make solar energy economically competitive with fossil fuels. But she also expressed satisfaction at having lived to see solar energy taken seriously, at seeing some of the applications she had worked on decades earlier finally being implemented commercially, and at knowing her research had contributed to a more sustainable energy future. Maria Telkes died on December 2, 1995, at age 94, in Budapest, Hungary, the city where she had been born nearly a century earlier. She had returned to Hungary in her final years, though she had spent most of her adult life in the United States. Her death received obituaries in major newspapers and tributes from the solar energy community, recognizing her as one of the pioneers who had made modern solar energy technology possible. Telkes's legacy is both specific and broad. Specifically, she holds more than 20 patents related to solar energy applications, thermal storage, and related technologies. She published over 100 scientific papers and technical reports documenting her research. She developed the first practical solar-powered desalination device, created innovative thermal storage systems using phase-change materials, designed the first modern solar-heated house, and contributed to countless other solar energy applications. But her broader legacy is in demonstrating that solar energy could work, that it wasn't science fiction or impractical dreaming, but achievable engineering using sound scientific principles. When Telkes began working on solar energy in the 1940s, it was a fringe topic that few serious researchers pursued. When she died in 1995, solar energy was an established field with university programs, government research funding, commercial applications, and growing industry. That transformation didn't happen automatically. It resulted from decades of research by pioneers like Telkes, who developed the science and technology necessary to make solar energy practical. Modern solar thermal systems, solar water heaters, solar heating for buildings, concentrated solar power plants, all build on principles and technologies that Telkes helped develop. Phase-change thermal storage, which Telkes pioneered in the 1940s, is now used in various applications for storing thermal energy and smoothing out supply-demand mismatches. Solar desalination, which Telkes developed for wartime survival, is now being explored as a solution for water scarcity in arid regions with abundant sunshine. Telkes's career also illustrates the long timescales often required for new technologies to be adopted. She developed practical solar heating in the 1940s, but it didn't become commercially significant until the 1980s, and mass adoption of solar energy didn't occur until the 21st century. Technologies often require decades between invention and widespread deployment, waiting for costs to decline, for supporting infrastructure to develop, for social acceptance to grow, and sometimes for crises or changed circumstances to create demand. The environmental legacy of solar energy, the field Telkes helped create, is now central to addressing climate change. Solar photovoltaic panels, while different from the thermal systems Telkes worked on, are now the fastest-growing energy source globally, providing clean electricity that displaces fossil fuel combustion. Solar water heating, solar space heating, and other thermal applications continue to grow. The vision Telkes had in the 1940s, that solar energy could provide a clean, renewable alternative to fossil fuels, is being realized, though decades later than she might have hoped. Telkes's story is also part of the larger history of women in science and engineering. She succeeded in fields that were overwhelmingly male, that often dismissed or marginalized women's contributions, and that erected barriers, both explicit and subtle, to women's advancement. She did this partly through exceptional talent and determination, but also through finding supportive colleagues, choosing research topics where she could work independently, and persistently publishing and patenting despite obstacles. Her success helped pave the way for later generations of women in engineering. The nickname, Sun Queen, that Telkes received in the 1950s was somewhat patronizing, emphasizing her gender in ways that male scientists' nicknames didn't, but it also reflected genuine recognition of her unique contributions to solar energy. She was, in many ways, royalty in the solar energy field, one of the founding researchers, someone whose work established key principles and technologies, and someone whose career spanned the field's development from marginal curiosity to serious energy source. Today, as solar panels cover millions of rooftops, as solar farms generate electricity for cities, as solar water heaters provide hot water, and as researchers continue developing advanced solar technologies, Maria Telkes's legacy endures. She saw what solar energy could become long before most people did. She did the hard scientific and engineering work to make it practical. She persisted through decades when her work was undervalued or dismissed, and she lived to see the beginning of solar energy's transformation from fringe technology to mainstream energy source. The Sun Queen built her kingdom brick by brick, patent by patent, paper by paper, over 5 decades of research. She proved that solar energy worked, that the sun's abundant energy could be harnessed for practical use, and that renewable energy wasn't just a dream but an achievable reality. Every solar panel, every solar water heater, every solar-powered device is part of her legacy, the realization of a vision that Maria Telkes championed when few others believed in it, the fulfillment of decades of work by a brilliant scientist who saw the future more clearly than her contemporaries and dedicated her life to making that future real.